White Sands Missile Range, New Mexico. Late in October of 1983, final preparations were underway for an above-ground high-explosive test, codenamed Direct Course. This event was part of the Misty Castle Test Series, sponsored by the Defense Nuclear Agency with 23 separate government agencies and 6 foreign countries participating. The primary objective of the test was to investigate air blast and ground shock effects of a simulated 1 kiloton nuclear detonation at a height of 166 feet. A secondary objective was to provide a thermal environment for selected experiments along with the air blast. Viewed from the top of the charge tower are some of the 200 separate experiments arrayed around the test bed. Since the Limited Test Ban Treaty in 1963, above-ground high-explosive tests are used to study blast overpressure and related effects. Empirical data can only be obtained from an actual high-explosive detonation in the atmosphere. To obtain such baseline data, DNA, the Defense Nuclear Agency, conducts high-explosive tests designed to simulate low-yield nuclear detonation air blast effects. Dice Throw in 1976 and Mill Race in 1981 have been recent tests. All were surface tests, with Mill Race also providing a simulated nuclear thermal environment. While Direct Course was but one in a series of high-explosive tests, it was the first height-of-burst test of this size ever attempted by the United States. Such detonations above the ground surface create unique air blast phenomena known as the Mach stem. The Mach stem effect begins sometime after the incident wavefront strikes the ground and is reflected upward from the surface. The incident wavefront expansion continues outward. At the point along the ground surface called the transition point, the incident and the reflected wavefronts combine into a complex wavefront known as the Mach stem. The intersection of incident, reflected, and Mach stem wavefronts is called the triple point. A complex wavefront in which 2 triple points occur is known as the double Mach reflection region. In this region, extreme turbulence and vortex action causes greatly increased dust pickup. As the complex front continues to move outward, the 2 triple points coalesce and continue to rise. The single Mach reflection region is formed, normally at incident overpressures below 100 psi. As seen in this actual test footage, the Direct Course detonation would allow detailed studies of this phenomenon on a scale not possible since the termination of atmospheric nuclear testing. As a test of this type had not been done previously, a proof of concept test entitled Pre-Direct Course was conducted in October 1982 using a much smaller 24-ton ammonium nitrate and fuel oil charge contained in a fiberglass sphere at a height of 57 feet. The tower and container assembly was a scaled-down version of the design for Direct Course. Key diagnostic instrumentation was evaluated both on an ideal reflecting surface and on a specially prepared dust surface. Of special interest was analysis of the dust-laden environment created by the height-of-burst detonation. The pre-direct course detonation successfully produced the desired proof of concept and met all objectives. Direct course testbed preparations commenced in January 1983, some 9 months before the scheduled event date. Air blast radials were prepared, a road network established, major cable runs in place, and instrumentation parks readied. Sections of the charge container were prefabricated and brought to the test site, where the laminated sections were fiberglassed together, making a hemisphere. The 2 hemispheres were mated to form the completed sphere. The 2 sections of the central supporting column were set in place. Then the polyester support netting was attached, and the finished upper tower was moved to a temporary footing near ground zero. The lower steel tower, once welded together, was raised and guyed to its footing. The last major step in tower construction was positioning the upper assembly. Lifting the 98,000-pound load and guying it down were a full day's operation. Meanwhile, other preparations were underway, such as construction of a DNA-developed thermal radiation source, or TRS, designed to study the effects of thermal radiation on a test object in a blast environment. A single TRS unit consists of 4 variably spaced nozzles and a central fuel supply module. To simulate the thermal radiation produced by a nuclear fireball, a high-pressure nitrogen source forces a mixture of liquid oxygen and aluminum powder from the supply modules together, causing an intense thermal plume when ignited. On direct course, 10 TRS units were placed just in front of some 23 experiments at various overpressure levels and thoroughly tested prior to placement of the experiments. The over 200 experiments to be evaluated were placed at predetermined radial distances from ground zero and oriented to obtain the desired data. These experiments were generally divided into 4 categories: civil defense and military structures, tactical military equipment and systems, hardened models of mobile missile launchers, and blast effects phenomenology studies. FEMA, the Federal Emergency Management Agency, participated on direct course with 43 various civil defense-related experiments. These 2 1/10 scale steel frame and concrete frame buildings located at the 50 psi pressure level were constructed to investigate structural responses of existing buildings. Failure modes, times of failure, and structure interaction with basements would be observed. Full-scale basement walls were tested. These reinforced concrete frame structures were built flush with the ground at 3 separate overpressure levels. Data gathered from these and model walls will give engineers the capabilities to harden existing basements for survivability. To provide further insight into different sets of collapse conditions and debris scattering, 2 buildings were constructed at the 30 psi pressure level. One was a single-story structure of reinforced concrete columns with clay brick walls. The other, a 2-story load-bearing masonry building. The movement of heavy debris was also studied by means of concrete cubes of varying densities and sizes. Scattering debris promotes the spread of fires started in a real nuclear detonation. A group of experiments were designed to investigate the effect of air blast on extinguishing fires. Preliminary testing determined the time debris had to be ignited before detonation. Investigations would determine at what overpressure levels fires could be extinguished by the blast wave. In a related group of tests, typical furnishings were placed in a room to be ignited prior to the detonation. These rooms would be partially or fully engulfed in flames like this one just before detonation to determine just what blast wave overpressures would extinguish the fires. Since industrial areas are expected to be prime targets in the event of a nuclear blast, a steel-framed light industrial structure erected by Waterways Experiment Station was at the 25 psi level to investigate the vulnerability of industrial-type buildings. Actual pieces of equipment were placed by FEMA inside the building, and other pieces were placed in the open. 55-gallon drums banded together to evaluate different storage configurations were placed at several overpressure levels. A number of civil defense and military shelter designs were also evaluated for foreign countries, including France, with this half-buried, self-contained personnel shelter, where mannequins were placed to investigate blast effects on persons. Other structures included a Swedish communications shelter housed inside this concrete vault. Federal Republic of Germany reinforced concrete shelter models, and various corrugated steel British shelters. Great Britain built a typical semi-detached brick house. In addition to the blast-induced failure mechanisms of the house, investigations were made on the survivability of mannequins placed inside several expedient shelters within the house. At the 150 psi level, this Norwegian fighting position was designed to investigate weapon and personnel survivability. Mannequins were placed throughout this hardened fortification. Additional foreign experiments included ammunition, fuel system components, light anti-tank warfare materials, protective clothing, and radomes placed throughout the test bed. Blast effects were also investigated on U.S. Army lightweight shelters. Made of fiberglass, corrugated metal, and foam, these fighting positions were tested at 4 different PSI levels. At the 1 PSI level, a foam military shelter was constructed by the Army's Civil Engineering Research Laboratory. In order to investigate their survivability, a variety of operating U.S. Army tactical systems and equipment were positioned at various locations. Included were the Army's Pershing missile system, a light armored vehicle, a multiple launch rocket system, the M1 Abrams tank, the Bradley fighting system, and an NBC decontamination unit. For comparison purposes, Soviet tactical and personnel vehicles were also positioned for blast effects studies. For the Navy, 10 different shipboard antennas and antenna components were mounted on a platform where they would be subjected to both blast and thermal effects. Direct course provided an opportunity to test cylindrical elastic plastic structures in a 40-foot square pool, 16 feet deep, constructed very close to ground zero. Anticipated overpressures with a trailing subseismic water shock wave would be greater than 625 psi. This view from the tower shows that 2 of the structures were floated on the surface and 2 were submerged. Since aircraft are especially susceptible to blast effects, an F-4 aircraft was placed in a free field environment, and another was placed in an open U-shaped revetment, both at the 6 psi level. Data was collected to compare each airframe's structural response in these different environments. Sited at the 10 psi level, 2 prototype hardened tactical shelters were also exposed to the thermal radiation source. Other Army tactical shelters, with and without equipment inside, were positioned at PSI levels from 10 to 2, all with side-on blast orientation. In order to investigate blast effects on hardened mobile ICBM launchers, models of various geometric shapes were placed at different orientations and pressure levels, ranging from 10 to 50 PSI. Evaluations were also conducted on full-scale vehicle-to-ground seals, friction enhancement techniques using models, and pressure venting methods. These tests will provide baseline blast effects data on vehicles to be used as hardened mobile launch platforms. Some models were mounted on tables to avoid the ground surface boundary layer. An area of major importance was the study of the near-surface dust environment. Previous investigations have shown that dust produced by a burst near the ground will be dense and highly degrading to electronic and mechanical systems, especially sensor systems. To help study these effects, a dusty area was prepared. Numerous dust and blast diagnostic measurements were taken in this area. Passive experiments studied the effects of dust loading, while optical instrumentation studied dust erosion mechanics. and light attenuation phenomena. Canadian beta ray and piezoelectric gauges compared dust densities and shock waveform between dusty and clean areas, while actively instrumented concrete blocks investigated the effect of dust loading. Air and air plus dust stagnation pressure measurements were made to derive dust loading as a function of time, while optical instrumentation was used as another technique to determine dust densities and mechanical properties. Other instrumentation was used to measure particle velocities, surface shear, and dust turbulence. Cloud experiments included the measurement of RF noise and the electrostatic environment generated by the dust, measuring dust parameters by means of radar, and determining dust-induced lightning and RF noise on the test bed. Measurements of ambient air entrainment and the dust cloud velocity flow field were also taken. One of the last experiments installed was a general-purpose radioisotope thermoelectric generator designed to provide electric power for interplanetary spacecraft. The unit was placed on a tower only 40 feet from the blast source, so it would experience incident overpressures similar to an accidental explosion on the Space Shuttle launch pad. With detonation diagnostic systems installed in the charged sphere, explosive loading began. The explosive used was ammonium nitrate with 6% fuel oil added. Each bucket of ANFO was sampled and weighed for quality control purposes. In all, 609 tons were placed in the sphere. By the 23rd of October, preparations were essentially complete. A full dress rehearsal of test day activities was conducted the following day. On the morning of the 26th, spectators gathered at the observation post, 4 miles from ground zero. As the countdown commenced, signals were sent out automatically by the computer. A few seconds prior to detonation, the thermal radiation sources were activated. Intensity of the detonation proved to be close to predictions throughout the range of PSIs of interest. As the dust cloud rose and dispersed, aircraft took photographs and dust samples of the cloud, as well as radar scanning measurements of particle velocities. Post-shot analysis of the site and the experiments began almost immediately. Some debris fires were extinguished depending on the PSI level and orientation towards ground zero. Behavior of the interior room fires was as predicted. Rooms totally engulfed in flames were not blown out by the blast wave. The room fire at 3 PSI was blown out, but later rekindled. Following photographic documentation of the dusty radial surface, experimenters began their recovery of data. Analysis of damages to civil defense and military shelters included immediate field inspections and photographic documentation. This included the lightweight fighting position shelters, most of which were destroyed at the 50 and 25 PSI levels. The dome structure made of foam failed, even at the low 1 PSI level. The French shelter entryway, subjected to overpressures above 55 PSI, was heavily damaged. However, the personnel compartment survived intact. All above-ground structures were heavily damaged or totally destroyed. The industrial steel frame building at 25 PSI was virtually leveled. Industrial equipment stored inside and outside the building showed that even at very high overpressures, damage was much less severe in equipment that had been banded together to prevent overturning. As expected, the 1- and 2-story buildings at the 30 PSI level were both destroyed. The roof slabs came virtually straight down as the cinder blocks were dispersed for great distances. Although there was less debris scattering from the reinforced 1-story building. The 2 4-story model structures located at the 50 PSI level were both destroyed as anticipated and provided data on modes and times of failures, as well as structure interaction with the basement chamber. All structures, even many hardened structures, suffered damage. The basement walls, which experienced 100 PSI overpressures, were cracked in several places. The model basement walls and the model shelters provided good response data. Recovery of the expedient personnel shelters in the British House took some time. 4 of the 10 mannequins survived the blast. Damage to the hardened mobile tactical shelters proved to be minimal, and thermal damage was non-critical. Although shelter walls deflected considerably, the shelters maintained their integrity. Reflected pressures in the Norwegian structure, constructed at the 150 PSI level, reached 500 PSI, indicating that no human would have survived. The 2 F-4 aircraft sustained limited damage and would have been flyable with minimal repairs. The aircraft moved about 3 feet horizontally, and excellent structural response data was obtained from both aircraft. The aircraft inside the open revetment did experience more vertical motion than the one outside, due to overpressure reflection from the berm. Hardened mobile launchers at the higher PSI levels were displaced from their platforms. Even the vented designs were significantly affected by the blast. A large amount of baseline data was obtained to further the HML development program. The direct course event produced few surprises. Behavior of the shock wave and the overpressures were within predicted parameters, although over a short range, incident pressures were greater than expected. Most equipment and experiments performed close to predictions. Damage to some hardened structures was more severe than expected. A tremendous amount of baseline data was obtained on dust and the resultant cloud. Damaging effects of the dust cloud can now be analyzed with greater certainty. Overall, the event fulfilled its objectives. returning the quantity and type of data required to continue to investigate the air blast and thermal effects of nuclear weapons. Follow-on high explosive shots will use the same test area, which was fully restored for future testing in the Misty Castle program.